All right, we've been talking about solutions, but we haven't really looked at what exactly happens when something dissolves in water. And that's what we're going to talk about in this video. We're going to talk about the solvation process and what is actually going on with the particles and the water molecules when something forms a solution. So when we use the term solvation, what that basically means is the process of surrounding the solute particles with solvent particles to form a solution. And solvation in water is called hydration. And remember, most of the time we talk about aqueous solutions, and water is our solvent. So when we look at things dissolved in water, we're going to be looking at the attraction between the positive and negative ends of the water molecule and the ions of the solid that's being dissolved, or if it's a molecular compound, then the molecules. We'll also look at gases being dissolved and how that is affected as well. So anytime we're talking about the solvation process or things becoming solutions, it's all about the attraction between the water molecules and the solute particles. All right, so let's look at an example here. Okay, so in this particular diagram, we have sodium chloride. Okay, so our little sodium ions are here and our chloride ions are the green ones. And as you can see, when sodium chloride dissolves in water, those ions break apart and they become surrounded by water molecules. Okay, now if you'll notice on the chloride ion, the hydrogen side of the water is attracted because the chloride is negative, the hydrogens are slightly positive. On the sodium ion, the oxygen side of the water is what is attracted because the oxygens are slightly negative, the sodium is positive, so we're seeing that attraction. And each of these ions gets surrounded by water molecules. That's what happens, and that's why when a solid dissolves in water, you can't see the solid anymore because we've actually split apart all of the ions. They're all separate from each other, and they're all surrounded by water molecules. Now, in the solvation process, we call the energy change that occurs when a solution forms, we call that the heat of solution. And just like in the last unit where there was a heat of combustion or a heat of vaporization, it's the same idea. And that heat of solution is caused by those attractions with the water molecules. For example, when sucrose dissolves, which is table sugar, there are lots of places on these sucrose molecules, and you can see, oh, go back. This whole thing right here is a sucrose molecule. There are lots of places for attractions between the sugar molecule and the water molecules. So that's what causes that heat of solution, is the attraction that we're forming between the water and the solute. Now, there are factors that affect the dissolving process, and you've probably run across these before. For example, stirring or shaking moves dissolved particles away from the contact surface more quickly and allows new collisions to occur, thereby increasing the rate of solvation. So when you put sugar in your tea, if you stir it, it dissolves faster because you're moving the particles around, you're increasing the contact with the sugar and the water molecules in the tea, and so it dissolves faster. Now that doesn't mean more can dissolve, that just means the stuff you put in dissolves at a faster rate. The same is true if you break the solute into small pieces. If you increase that surface area, then you're going to have more collisions, increasing the rate of solvation. Again, you can't dissolve more of it, you just dissolve what you have faster. And when we're talking about a solid, okay, if we increase the temperature, it will also dissolve faster. We're going to look at what else temperature can change, but if you're trying to dissolve sugar in hot tea versus iced tea, you're going to have it dissolve a lot faster in the hot tea because those molecules are moving around more. So it's similar to stirring or shaking. So those things can make a solid dissolve faster in water. Now, let's talk about the term solubility. Okay, there are some solids that dissolve in water and there are some that can't. An unsaturated solution versus a saturated solution. Unsaturated solutions contain less dissolved solute at a given temperature and pressure than what we consider saturated. And in a saturated solution, it contains the maximum amount of dissolved solute for a given amount of solvent. that should say solvent right there, at a specific temperature and pressure. Okay, that should say solvent. All right, so let's take a look at our little graph that we have here. So let's look at calcium chloride. You can see at 0 degrees Celsius, that's how many grams of calcium chloride, 60 grams, will dissolve in 100 grams of water. If we increase the temperature to 20 degrees Celsius, then a little more than 80 grams will dissolve. Okay, so as we increase temperature, more of that particular solid will dissolve. Now, what happens if we dissolve almost 100 grams and then we cool it back off? Well, that means some of it's going to have to crystallize out because it can't dissolve anymore. Solubility is based on temperature. If you take a look at NaCl, okay, that has a very small slope. So we're not going to get a lot of increase in solubility as we increase temperature. And actually, if we look at this blue line here, there are a few solids that decrease their solubility as temperature increases. So just saying that if you increase the temperature, the solid will dissolve more, that's true most of the time, but not all of the time, okay? And it's true more for some compounds than for others. And we're going to do a lab with this specific one, potassium nitrate, and we're going to figure out what its curve looks like on a graph, just like this. All right, let's talk about something called a supersaturated solution, which actually contains more dissolved solute than a saturated solution at the same temperature, which seems impossible. Like saturated means the most, right? Well, if you want to form a supersaturated solution, you actually form a saturated solution at a high temperature, and then as you slowly cool it down, if you can do it carefully enough, you'll actually keep all of that stuff dissolved when it shouldn't be dissolved. Supersaturated solutions are very unstable. Any tiny little disruption will cause all the excess to crystallize. So, you know, if there's a scratch in the glass of the beaker, if you drop in a tiny little crystal, any of that will cause that supersaturated solution to crystallize out all of the extra. And as you can see here, we have a chart of solubilities. Okay, so most of these things, most of these compounds will increase their solubility as temperature increases. You can see some of them don't, right? Some of them down here at the bottom, if you look at the last three, these are all gases. Okay, now if you'll notice for the gases, the opposite is true of solids. As you increase temperature, solubility decreases, and we're going to get to gases here in just a minute. So when you're thinking about dissolving solids versus dissolving gases, they're going to have different relationships with changing the temperature. Okay, so let's talk about gases. We're going to look at Henry's law, which states that at a given temperature, the solubility of a gas in a liquid is directly proportional to the pressure. Okay, and here's our formula for Henry's law. So gases are less soluble in liquid solvents at high temperatures, and the solubility of gases increases as its external pressure is increased. Now, let's talk about what that means. And the best way to think about dissolved gases is to think about soda. Okay? A soda has dissolved carbon dioxide. That's what makes it fizzy. And if you want to keep your Coke from going flat, what do? Well, you keep it in the refrigerator. At low temperature, that carbon dioxide is going to dissolve more than at high temperature. So keeping soda cold will keep the carbon dioxide dissolved. Gases are less soluble at high temperatures. Also, if you want to keep your soda carbonated, you want to keep the pressure above it high. So when you first open a brand new bottle or a brand new can of Coke, and you take the cap off and you hear that noise, that escape of gas. The reason that's there is because that little space above the liquid is actually filled with carbon dioxide when that soda is bottled, and that carbon dioxide keeps the dissolved stuff in. It keeps the gas from escaping from the container. So when you let out that carbon dioxide, you are releasing the pressure, which means you're going to get the fizz. The gas is actually less soluble. So let's take a look at using Henry's law in a calculation. It says If 0.85 grams of a gas at 4 atmospheres of pressure dissolves in a liter of water at 25 degrees Celsius, how much will dissolve in a liter of water at 1 atmosphere of pressure in the same temperature? So our solubility over pressure. So it will have 0.85 grams will dissolve at 4 atmospheres. We want to know how much will dissolve at 1 atmosphere. So if we solve for S2, we would cross multiply, solve for S2, and that gives us 0.21 grams of our gas will dissolve at 1 atmosphere. Okay, so as you can see, decreasing the pressure decreases the solubility of the gas. And we're going to see a lot of examples of these things in class on Monday. I'm going to show you a bunch of demos and a bunch of examples of solids and liquids dissolving and gases dissolving and how these things all work together.